Math 2414, Trigonometric Integrals, Integrating a Product of Sines and or Cosines, Part 4. I'm pretty sure there is going to be a Part 5. It's just like it never ends. It's like an infinite series. That'll be funnier when we get to Chapter 8 in the book. Integrating a Product of Sines or Cosines, Part 4. So far, we've developed a technique for integrating this product when at least one of the powers is odd. And I've summarized it over here. Let u equal the other trig function. In other words, if one has an odd power, let u equal the trig function on the other one. And then you borrow from the odd power for the du package, and then you use a Pythagorean identity to rewrite the unwanted trig functions. You don't have to memorize these steps per se, you just got to do what makes the problem work by identifying the obstacles and knowing the steps for overcoming them, like using the Pythagorean identity. But if both powers are odd, then I would let u equal the trig function with the greater power. It simplifies the algebra after making the substitutions. But what if none of the powers are odd? What if they're all even? Plus, I've been saying and or, implying it can be one or the other, not necessarily both. So let's take a look at the simplest example of integrating trig functions with even powers, one trig function to the second power. Now some of you might start thinking, wait a minute, can't we use the power reducing integral that was in a homework assignment back on the integration by parts? And the answer is of course you could, assuming that you have that memorized or at your disposal. But we're going to use a different strategy, although I'm okay with using the power reducing formulas created in the integration by parts homework assignment or the integration by parts video where I created one. You created the other. But if both powers are even, we can use power reducing formulas. The last video in the trig identity review videos prior to this, if you're in my class, prior to this in the module for week 2. Recall that one of those identities said that cosine squared was equal to 1/2 plus 1/2 cosine of 2x. Again, all I did in changing this integrand to that integrand was use a power reducing formula. It's a trig identity. It reduces the power by rewriting cosine squared as an expression in terms of cosine of 2x. Now that knocks the power down and it makes this integrable using calculus 1 techniques. In fact, we can almost integrate this instantly right now. The integral of 1/2 dx is 1/2 x. But when we integrate cosine, well, first off, the integral of cosine is sine. Okay, so we're not going to pick up an extra negative. But if we were to integrate, well, and we have the 1/2. But if we were to integrate using a substitution of u equals 2x, and du would equal 2dx, and so in order to pick up the 2 on the dx, we would have to balance it with an extra 1/2. This is something that I kind of alluded to in previous videos, that if you're doing an integration and your substitution's derivative is a constant, then just integrate like you normally would and balance with the reciprocal of that constant. It's to counteract the effects of the chain rule if we were to check this. If we were to check this derivative, we would have to eventually do the derivative of 2x as the last part of the chain rule. That would pick it up at an extra 2, which would cancel that 1/2, leave us back with a 1/2 plus c because it's an indefinite integral. And so our answer would be 1/2 x plus 1/4 sine of 2x plus c, which is a perfectly acceptable answer, even though this trig function's argument, 2x, is different than this trig function's argument, just x. I suppose you could bust out a double angle formula to knock this back down to x, but the obstacle here was the integral, not the form of the answer. All right, so yeah, and if you're still reeling about power reducing formulas, then go watch, and if you're not in my class, you can search this on YouTube, Math 2414, Review, Trig Identities, Power Reducing Formulas. I know it's a lot, but you can always go back and listen to it again, or turn on the captions. Math 2414, Review, Trig Identities, Power Reducing Formulas, and go watch the video on that. All right, now this seems like a short video, and if I were to check the time, I'm sure we might have hit the 5-minute mark. Nope, not quite. But this isn't the only integral I wanted to do in this one. When you're integrating a single trig function to a power, it's not that bad. but it can get pretty ugly depending upon what all you have. I was debating whether or not to do one more example where things are going to get uglier by attaching a sign on here with an even power. But I don't want to use the same even power as before, because as I'm kind of foreshadowing here, if the powers are different and if the powers are the same but both even, you got a couple of options. So if I want another power that's even but not 2, I guess I have to use 4. All right. If you're integrating a product of sines and cosines and both powers are even and the powers are different, then use power reducing formulas, which doesn't seem like a big deal. The power reducing formula for cosine squared is still 1/2 plus 1/2 cosine of 2x. And the power, we have sine to the 4th x. We have to think of that because our power reducing formula is for sine squared. Sine squared x, sine to the 4th x is sine squared x squared. Unfortunately, our power reducing formulas are for powers of 2, sine squared and cosine squared. So I have to rewrite this as in terms of sine squared. The power reducing formula for sine squared is 1/2 minus 1/2 cosine of 2x, but that has a square on it. And right there you can see why this is about to get pretty ugly. That's a product. We don't integrate products, we integrate sums and differences. So, and by the way, there are exceptions to that rule, like every rule, but in general, if we're integrating a product, one common strategy is to get rid of the product by multiplying it out. But to multiply this out means we would have to write this parentheses twice and then begin foiling all 3 of them. And it's going to look pretty ugly, but it's not going to be really as bad as it seems if you make some convenient moves. For example, I am going to write all 3 parentheses. But you'll notice I could factor a 1/2 out of all of them. I could factor a 1/2 out of this, it would leave 1 plus cosine 2x. 1 plus cosine 2x. And I'll put the 1/2 out here. And I can factor a 1/2 out of this and leave 1 minus cosine 2x. But then that 1/2 would multiply by this 1/2 to make it 1/4. But then I can factor another 1/2 out of the second of these parentheses, leaving 1 minus cosine 2x, and another 1/2 times 1/4 would make it 1/8. So anytime you're using these power reducing formulas, you will have the option of factoring out a 1/2, and sometimes it's not a bad idea. So factoring out all the 1/2 leaves us here. We still have a product. Let's just attack it one pair of parentheses at a time. This one's actually pretty easy. This is just going to be a difference of squares. From an algebra perspective, if you multiply a plus b times a minus b, you always get a squared minus b squared. Most people recognize this in reverse as a squared minus b squared factoring into this. Well, it's a two-way proposition. So we can multiply that pretty quickly and say 1 squared, which is 1, minus cosine squared of 2x times 1 minus cosine 2x. We still have a product, and we have to integrate. We have to multiply it out before we integrate. So 1/8 integral. All right, let's FOIL this. First, 1 times 1 is 1. Outside, 1 times minus cosine 2x is minus cosine 2x. Inside, minus cosine squared 2x times 1 is minus cosine squared 2x. And then last is negative times negative is positive cosine cubed 2x. All right, we've completely destroyed the product, which means we can now integrate this one term at a time. And as you can tell, this problem just keeps getting worse. Well, this integral's not bad, that one's not bad. We know how to tackle this one because it's what we did before we tacked on here. And this one is actually just an odd power, so we have a plan for attacking that. One thing you'll notice in integration is you fix one problem and you create another. But usually what happens is you get to a point where you create a problem that you know how to resolve. I know how to do all of these. Am I going to take time to integrate all of them? Yeah, I think I am. But I want to move this up here because I'm going to need the space and there's too much important stuff for me to not erase. So let's just move this up. 1/8 integral 1 minus cosine 2x minus cosine squared 2x plus cosine cubed 2x dx. All right, let's do this. Let's integrate it one piece at a time, starting with the integral of 1. That's easy. Let's switch colors. Let's go to green. If we do the integral of 1 dx, that's not even worth fiddling with. It's just x. Don't worry about the plus c. We'll pick up the plus c at the end. So this integral's done. Now for the integral of cosine of 2x, that's pretty easy. I was debating whether or not to bring the minus down. You gotta be real careful when you pull a problem apart to not lose any pieces. So I'm gonna put boxes around the things that I'm focusing on so that when I put it all back together, I know what I left behind, namely the pluses and minuses. Integral of cosine of 2x dx, this is pretty easy. The antiderivative of cosine is negative sine. We would do a substitution with u equal 2x, so du would be 2 dx, and we would balance that with the reciprocal of 2. We can take the derivative of that real quick to make sure that it is cosine 2x. Wait, it's not. Thank goodness I took the derivative. The derivative of sine is cosine, and we would keep the negative. Shame on me. I don't care how good you are. We all make mistakes. But I'll check it again. Derivative of sine is cosine. Chain rule would pick up an extra 2 to cancel the 1/2 and take me back here. So that one's okay. The integral of cosine squared of 2x dx, we have a strategy for, which is to use the power reducing formula. And here's where you have to really know what your power reducing formula is saying. Power reducing formula for cosine squared says 1/2 plus 1/2 cosine of 2 times the argument. The argument is already 2x, so when I multiply it by 2 again, I get a 4x dx. And at that point, it's pretty easy to integrate. We get, and I'm thinking back in the cosine squared, I might have had a negative off kilter. I'll have to go back and watch the video to see, and then type a comment in the description of the video if I did. But anyway, if we integrate this, the integral of 1/2 is just 1/2 x, so not a whole lot to look at there. And here, the integral of cosine of sine, substitution on the 4x would bring in a 1/4 when we balance out the du. In addition to the 1/2 that's already there, would give us 1/8. And by the way, I'm not saying you should integrate these things this quickly. I just know that this is a long problem. You write all the details you need to write. And the last one is the integral of cosine cubed 2x dx. But this is an integral of sines and or cosines to an odd power, and I have a strategy for that. Let u equal the other trig function, and you might say, but there's no sines, and you would be correct for now, but I borrow one from the odd power for the du package. So let's go ahead and start by saying let u equal sine, in this case sine of 2x, then du is equal to the derivative of sine's cosine, 2x, chain rule says times 2 dx, so we need to build this du package. Let's peel off the cosine, put it over here. Cosine of 2x dx. That would leave cosine squared 2x. But we use a Pythagorean identity to rewrite that one, so let's go ahead and rewrite that one as 1 minus sine squared 2x. And now let's focus on the du package. The du package means a dx, which we have, a cosine 2x, which we have, and a 2, which we don't, but the 2 is easy to sneak in there. Should have anticipated and left room. Put a 2 and balance it with its reciprocal. And so now we have all the contents of the du package, all that would become du. Sine squared would become u squared, and so our integral becomes the integral 1/2 integral 1 minus u squared. All this becomes du. Let's make sure I pull that off correctly. Yep, and now the integral's easy. 1/2 times u minus 1/3 u cubed. And then if we distribute it and change the u's back, we get 1/2 times u, but u is sine of 2x, so 1/2 sine of 2x, minus 1/2 times 1/3 is 1/6 u cubed, so sine cubed of 2x. And now that we've got the answers to all 4 individual integrals, x, 1/2 sine 2x, 1/2 x plus 1/8 sine 4x, and then this last one, which took a little bit more work, 1/2 sine 2x minus 1/6 sine 2x. Now we can string them all together. Therefore, our answer is equal to the sum of all those plus a c, plus c. Let's gather like terms. We got an x, we got a 1/2 x, those are the only x terms. X plus half x is 3/2 x. Let's gather our sine 2x terms. We have a 1/2 sine 2x and another 1/2 sine 2x, so that makes one of them, so plus sine of 2x. Let's gather our sine 4x terms, which are here. It's the only one, plus 1/8 sine of 4x. Let me take inventory. We've taken care of u and u, u and u and u, and the only thing left is the minus 1/6 sine cubed 2x, and plus our constant. Well, that was interesting, but it shows you that you can't just look at a trigonometric rule and go, oh, let me just do this little thing and everything's going to be okay. Some of them drag out. And there was another one that I wanted to do. Oh, there is one that I'm going to do. It's going to be part 5, and it's going to fill out this. Really, this will suffice. This will always work. If the powers are different, you can always use the power reducing formula. So really, I'm going to just change this to comma, use power reducing formulas. But I owe it to you to show you something. So we'll just make that an asterisk and say if both powers are even and the same, and in the next video I'll show you a little trick that you can do to integrate that. But again, the trick doesn't have to be used because you can just do what we just did here and then buckle up because it's going to be a bumpy ride.